Every time you chat with ChatGPT or see AI writing code, behind the magic there's PyTorch, the engine that teaches machine to think. But what if you could build your own LLM from scratch, step by step? That's exactly what this series is about. Everyone uses the LLM, but in this series, we are going to build one from tensors to transformers. We'll go beyond the tutorial and actually make PyTorch speak. I used to think LLM were just too big to understand, just buzzword and black boxes. Then I discovered PyTorch and everything clicked. In this series, I'll show you how it all connects. No bluff, just pure AI engineering. And we are going to together learn all of the fundamental that is required to build scalable machine learning system, and you are going to witness how your understanding changes over the series. To use GPUs, and not everyone will have the access to those machines, so we are going to use the Google Colab for learning all of the PyTorch. And this is free. You can make your account here. How to get the access of GPU? You'll need to click on the runtime, then change runtime type, and then select T4 GPU, then save it. So Google Colab give you generous free tier, and it'll be more sufficient for this tutorial. First thing first, let's install the PyTorch. You can code along with me. So let's do capture, and let's do pip. Let's install. We are going to need transformer, and we'll go with the version 4.4.1. If you don't want to expect any errors, you should also feel free to use same as my versions, so that it's easier to replicate. And let's go for any version higher than 0.27.2. So by default, the Google Colab comes with and PyTorch installed, which is going to be sufficient for us. So now that you have your runtime setup done, you have done your transformers there, and this is also installed. So the first step in the ABC of this series is going to be how can you load a language model into your GPU for faster inference. And note that we are loading model, and we also need to load tokenizer separately, although it's not necessary, but it becomes very useful, you'll see in this series. So from transformers, let's import transformers. Let's import auto model for causal ML, causal LLM. So first L is small, second is bigger. Auto tokenizer. Yep. And so this is going to import the transformers classes that will be useful for us. Perfect. We are good with it now. Let's load the model. Let's store it in the model variable. Model for causal LLM from pre-trained. How can I turn this off? I don't want this AI suggestion. Ooh. Tool setting editor. Setting editor. Show context power. No, we don't want. Yep, I think now we'll be able to code perfectly. So from pre-trained, still happening. Gate code completion section. Tool setting AI assistance. Editor. I believe now it's stopped. So let's use Microsoft's Phi 3 model, which will be comfortable to load in this 16 GB of VRAM. Microsoft Phi 3/mini/4K instruction. I think it's instruct. We'll check. That's the correct model that I remember. So you should also have your Hugging Face account setup done. There you can search for any model that you like. So ours, this is the model that we are going to do. So let's make sure that you have typed it correctly. You can bring any model of your choice. Now the second argument is important. Where do you want to load this model? And whenever you say I'm writing as CUDA, that means that I want my models weights and biases uh, be be sitting in the GPU RAM. And then there is also it expect us to also tells the data type. So it's because it changes based on which model you are loading. So you can mark this as auto, and it will be auto configured. So trust remote code is true, is false. Yeah, so we don't want that. I believe it's going to load the model. Meanwhile, uh, let's load the tokenizer. Auto tokenizer, auto tokenizer dot from pre-trained, and let's use the same model. Llama 3. Usually, this is for them. You'll have to type the same string, and this is what this is going to do. It's going to load your model and tokenizer, and that's pretty much how you bring your model and tokenizer for you locally. Now what although you can use the model and tokenizer directly, but it's much easier to wrap them into a pipeline object. So where can you find this? So from transformers import pipeline, you can directly bring it, and then let's create a generator pipeline, which is in the pipeline you'll have to specify the sequence and the task. If it's a general task, then there are the handlings are being done at the PyTorch level. Since this is the first tutorial, so we are going to use the inbuilt one. Later on, we will be building our own pipelines. So, and then you have to specify which model. So what it is going to do, it is going to make two execution for us. One is generating the tokens and then passing it to the models. Tokenizer, and let's also return full text. So return full text. Let's not return full text, but let's define the max new token to be, let's say, about 700, and let's do sampling. Let's not do it. Yeah, so this is going to be the generator object, and after that, once that is done, we are going to call it. So for that you'll need the prompt, the input, the query for your model. So now let's define the message template for our model, and it's going to be an array. The first is the role is going to be of user, and let's give this as context, as tell me the capital of USA. Let's say if it's able to do it, and then output, let's get generator, and we're going to pass the message inside of it, and then let's print out the output. So output is an array, usually the first value, and let's get the generated text. So because we don't want the other things, so let's run it. So did we not pass? Each tick must have a role and content key. Did I? Oh, sorry, I passed that as the context. It should be content. So it's fine. It's good that errors are coming while we are learning. Will show up. All right, so for this model, I believe that argument is not in use, but that's fine. Maybe that's some other arguments that we need to pass. So there you go. You can see the capital of United States is Washington DC. It's not part of the US. It is a federal district, which means it directly governed by the US Congress. Washington DC was named after George Washington's first president of United States. And let's look at the RAM usage. So the GPU RAM is about 7.3 gigabytes, and it has taken about 40 gigs of disk storage. And system RAM is about 6 GB. So what happens when we ask it to run for long? Write 8,000 word stereo story. Let's see how the GPU, if there's any spike in the usage. I believe it's quite stable. Yeah, so it's done. So nothing, just the system RAM increases a little bit, and it printed something, right? Which is not the scope. I mean, what we wanted to learn is like how can you bring any model from Hugging Face, load it in your environment, and then in the next chapter we are going to learn more complex things. And this is the hello world of this series, you can say. Stay tuned. Thank you for watching. They are the most important part in understanding the functionality of any transformer models. So whenever you see any word like embedding tokens, what is happening? Like if you can see from this diagram, this is the sequence of inputs, and it is getting mapped to a vector. So this mapping, uh, which is something very important for transformers, and this is something which is called the input IDs that we are doing here. And before this ever gets used for any transformer model, it is going to be added with the positional embedding. So if you can see what is happening here, this is your token embedding, and this is your positional embedding. You are going to take one vector from here, from left and right, and do the addition, and that's how you form the tokens from there to embedding. So token is just a single number, whereas the embedding is a two-dimensional array. You can say you can. So it has the C column and C rows and T columns. So this also depends upon the size of your embedding and the number of tokens that has been presented. So now let's see what we have done till now. We have done our installation, and we have loaded. In the previous session you have seen how to load a model, and through the with the help of pipeline we have run a simple text generation pipeline. So now we don't want that. We are not going to do always that easier. We are going to deep dive and look inside what is happening. So let's go to the stage where we can see these things, like from this English word, how the tokens are being getting generated. Let's see them. So let's uh, so for that will be done with the tokenizer. So I am actually loading the model again, just in case, so you can ignore it, just to so that it saves our time. Yeah, now, so from tokenizer, we'll pass this prompt: write an email for tragic gendering mishaps, explain how it happens, and this is the assistant tag, which means after this tag the generation should start. So we pass our prompt, and then we ask to return the tensors. PyTorch tensor dot input IDs to CUDA. So you need to, so this input ID generation happens at the CPU. So we'll need to send them to our GPU. Here you can see these are the mapping of these tokens. This maps, some word maps to 14350 and like that. So now let's see how the words are getting generated from the model. So for that generation, so we'll call model dot generate, and we can pass. There you have to pass the input IDs. It's not model directly don't take the word, instead it takes the input IDs. And let's see if the generation is successful. Perfect, it is generating the output for us. And let's do one thing. Let's ask our tokenizer to decode the generated output. So let's print tokenizer dot decode generated output. Yeah. So although Google Colabs does that for us, but this is how it's done. This used to be the prior version of Transformer, but right now the current version of Transformer handles pretty much all of it. So now I'm actually more interested in the in seeing the how does the tokenizer is actually tokenizing our input sentences. So let's do iterate in for the input IDs. Let's see what are these things meant actually. Like 14350 maps to what English word. This is something that I wanted to understand. So for that, you can go decode and you can pass the ID. Perfect. So see, now the mapping is like this. And if you can see, the tragic has been splitted as track and IC. So this is something the tokenizer responsibility is to do that. And you can like from what now what I wanted you to show, how can you compare how can we compare the trained LLM tokenizer. So from transformers, let's import. I think we have done importation. So like it would be better if you can see them as the color list of how things are being generated. So I have made an helper function which exactly when you pass them the model, based on what model, how the tokenizer is working. So this function is just mapping the colors based on how tokenization is done. So I have one prompt. Let's see. This prompt has everything like emoji, capital letters, and expression, mathematical expression, and all. So let's see how uh, with the help of this show token function will it be able to show us how the splitting of tokens occurs. And let's do it. We can pass this, and let's look at the BERT models, how their tokenizer does the tokenization of this word. I believe it's the spelling issue. BERT base. Oh, sorry, it's yeah. So it's bringing the BERT tokenizer, and see how the tokenization is starting. Start with CLS, then English and capital. Then it's breaking capitalization as ijation hash hash, and then next line as UNK show token false none. So show token false. So it has pretty much ignored this emoji. So I believe this model won't be able to perform well on such given languages as well. So this is a foreign language, so it was not able to tokenize it. And if you can see how it has tokenized every word from numbers into decimals expressions as differently. So to compare this, let's bring GPT-2 tokenizer and see, because I just wanted to bring first a simple model, so that once we bring a difficult, I would say a more capable model, it should do a better. Perfect. Here you can see now it has respected the formatting. So GPT-2 is quite better model. And let's see one more example. So you can play with different models, how they are doing the tokenization to understand this. So let's bring Google's one of the model, Google Flang T5. Let's see, that would be interesting to watch. Yeah, so it's not that good compared to GPT-2. The tokenization, I won't say, but here it makes much more sense how the tokenization has been done. And you can try a lot of others, any models. So let's take this tokenizer from our model that we are using previously, Microsoft Y3, and let's go there and let's run it. It should also, it's also doing as good as GPT-2, which makes sense. So this is a good exercise in learning how under the hood tokenizer itself is working. Now, so this is how you done the splitting. How will you do the contextualization of this I mean, the contextualization. How will you contextualize the word embedding for a language model? Like, let's say smaller model. Let's take an example, BERT. So for that, let's do one thing. Let's bring the Delta base model, and let's see the output shapes in terms of tensor, like what is the tensor size, output vectors, how does they look. And this will give us more idea, like because understanding the dimension is very important when learning the transformer or the PyTorch. Import auto model, and let's bring the auto tokenizer this time, and tokenizer Microsoft debug database, and let's also load the model. So from auto model dot from pre-trained, and then it's the same thing till Microsoft. The model we can change Delta v3x small, I believe. And let's do one thing. Let's get some tokens. So in the tokenizer, let's pass the word that we want to tokenize, hi you, and let's return the tensor. And let's also collect the output. Let's expand the tokens. Perfect. So it's bringing the model. The model isn't that big. I believe it should be done very quickly. And once it's done, so we have what I'm interested in first, seeing the output shape. What is the dimension? So I believe this is done. So dot, how do you see the output as dot shape? And so it's giving us the tensor. This is the dimension, and the 384 is the, I believe, size of the embedding, and 6124. So I believe it has broken that into 6 tokens, and this is the dimension. Let's see. Let's actually see. No, I believe it's from the output. So let's do one thing. Let's debug it, and let's go inside the tokens. ID is 0, and let's print, because we just learned above how tokenize dot decode. Sorry, it's 4. Yeah, so it has broken that as how are you, and I think it is 4 sentences, and the CLS and separator it is counting, so that's how it becomes 6. Perfect. Now let's see the output. So it's a tensor, and I believe this is going to be 318 dimensions, and 1 2 3 4 5 6. Perfect. So that's something we saw it from the shape, and you can literally just see it if you're interested, like what are the tensors value. So that's also present. Now this is for uh, like, now let's understand the text embedding for sentences and also for whole documents. So let's bring the sentence transformer. Sentence trans. Let's import sentence, and then let's bring a sentence transformer. Transformer all net mpnet base v2. So they are useful in doing the text embeddings. and we can convert, this is a text to text embedding model, so we can extract the vector from this. You pass them plain text and you get back the vectors. So let's see, it's hi, how. So it's bringing the model. It's about 438 MBs, and I think we have now the vectors. So let's see the shape. So 764 vectors it has created, the embedding of that much length, which is kind of cool. And there is also one library which is called GenSim. There we can do the word embedding beyond the LLMs. So I'll also show you how can you do that. So from GenSim as API, and let's API dot load. Let's bring the Glove model. Glove Wiki Kika Word 50. So I believe GenSim, no module in GenSim. Let's install it. Now we should be fine. So here what I wanted to show you is how the words are related in the embedding space. So let's say if we say the word laptop, then what are the similar spaces word in that model? And so for that, let's call model most similar, and we can pass model as, let's pass the AI. Let's see what we get back and how many. Let's get top 10 to be fine, I believe. So once it is done with what are the similar word related to AI, and let's see. All right, AI is not present, so let's use the word car because it's a very old model. So car is pretty much related to truck, cars, vehicle, driver, driving, bus, vehicle, parked, and motorcycle. So in the order of the similarity. So that's kind of cool. Like, and you can make even. So this is the example of the word embedding. Similar way, you can have the voice embedding as well, and you can also have the word to vec model bring, and that performs the most similar. This same thing from Gensing. What you have to do? So let me show you from. If your task is to do the similarity on the embedding, so there is one model also called word to vec, and you can bring that, and that model. So let's bring what models to bring, and then you for this one you actually need to pass this a list of uh, f- a list of vectors such so that it can do perform the embedding. For now, I'll leave this as an maybe an assignment for you all to try on, because I really wanted to uh, sh- go over to the next step, and we can look onto the next use cases of how can you build uh, like looking more deeper inside into the language model architecture with the help of PyTorch. So in the next video, we are going to see the input and output of a trained transformer model, their architecture, how can you see what layers they are using, and like the decoding methods, probabilistic distribution, sampling, decoding, a lot of more thing. And one of the most important thing is the key value caching for faster generation. So thank you for watching this session embedding, and now let's deep dive more into the architecture of the transformer model. So here you can see after the calculation of the embedding, and adding with the positional embedding, we are passing this embedding to the layer normalization, which does this mathematical formula, like it calculates the mean, variance, and then to the normalization according to that. And after that, if you can see, there are several vectors which are as q, k, v vectors, and then they are multiplied by their respective uh, QKV matrices, and from this calculation, they are being from basically they are being multiplied to calculate the attention matrices, and then projected back as the attention residual and the attention output. Then from there it goes to the MLP layer. From there you have up and down projection matrices. Uh, so there are up and down projections, and then subsequently it moves to another transformer block where the same thing KQV vectors are there, and same thing up down projections, and this gets repeated. This is the nano GPT-3 architecture, but let's say you are interested in seeing how any particular model that you are using, how their architecture looks like. So from the first session, we have learned how to load the Microsoft 5.3 model. And so this is the same code that loads the model and the tokenizer. In the last session, we have seen how to actually look at the deep inside the how tokenization work, how different models does different tokenization. So it's very easy to see the architecture of any model. So you just call the print method, and it shows the all of the uh, operation that this model is performing. So it's a model 5.3 model, the position, this embedding layer, and after it has the module layer. This is a decoder based architecture, so it is a 32 multiplication of these, meaning there are 32 subsequent things. So for example, if you can see, this was one and then there was another, so same way there will be 32. And then there is the self attention layer, the output projection, the KQV projection, and then there is the MLP layer, the layer normalization. We have seen this one, and the residual dropout, then the final normalization, then rotatory embedding, and then the linear attention head. So that's how this model is being made. And you can also look at their hyperparameters and all to get more even understanding. But this is how pretty much you can see every models that you have loaded into your environment. You cannot see for GPT-5 and 4 unless they disclose it, but pretty much for all open weights model, this is how you can see them. So now what we are more interested is how this when you see, if you go to very last of this model and coming here after the layer normalization, this is, if I will be able to zoom it properly, you can see if you are able to see it, the logic softmax, how this everything words and all converts back to actual word that needs to be predicted. That's something we'll need to understand, like how choosing a single token from distribution, the decoding works of a tokenizer. So let's call the input the let's ask this as a question, the capit of USA, the same thing that we asked, and then let's collect the input IDs. So from tokenizer we can pass the input, return tensor as PT. Let's collect the input, IDs, and let's also bring input IDs to the CUDA. And after that, so this till this point the input has been tokenized. Now let's pass this to the model and get the output. Dot believe it is, and so what I am trying is to get the output of the model before this LM head, and I'm just breaking it. So because then and only we'll be able to see the probability distribution, and from the LM head we'll get the output as you can see. LM head output can call model.lm head. So we can pass the model output. So this is how I was able to know like till which point I want the output. So till model I want this to be executed, and from there LM head to LM head output. So let's run it. Sorry for this typo. Return. I believe this is the correct one. Yeah, perfect. So we have captured the output in two phases, till the model and after the model to the final output, so softmax output. So let's get the output token IDs. So it's LM head, and from the last one let's bring the highest probability, argmax minus, so the highest one, and then we can use tokenizer to decode uh, this token ID, because it will be a number and it will make more sense. Alright, so it says the capital of USA is, so let me do is, then it should tell Washington. So you see, this is how the uh, auto-regressiveness is coming. So if I would have passed the is back to the input, and then it's doing the completion. So now let's do one thing, and let's see the shape of it. 0th dot shape. So it's a tensor of size 153072. Perfect. And now I'm interested in the shape of the LM head. So it's also same, which is not surprising. So this is how I've just given you one of the ways how can you break, and basically you can get the output till model layer 31 33. How does the output looks, and from there if you do LM head and see the output. And so this is what I wanted you to know, like you can go this much deep into the models when they are doing the generation. So it's not just the black box, everything is present in front of you, and with the help of transformers and PyTorch you will be able to in the most of the cases you will be able to see how things are working. So and then the next step is where I want you to pay attention, is how can you speed up now that you know the architecture and all, how can you speed up the generation. So something is called caching of KV, keys and values. So that's we are going to see. So let's write a message. Write a very long story about a lion in woods. And let's write 1,000. So this is something like I'm asking it to generate more, so that I wanted to show you how much time does it take for generation when you are doing I mean, if there's KV caching is enabled and if it is not. So generated output, since we have defined the model, so let's use it. Model.generate, or 1 second, we need, let's combine here input IDs and then tokenizer. You can pass the message turn tensor dot input IDs, and then same thing, pass the input ID to CUDA. Perfect. So we have generated the, and then we can use the collab macro as, let's measure how much time on an average per loop. I will do this multiple time, and let's see the median standard time for the generation. So let's get the generated output is model dot generate input IDs, and we can pass, we can, what we can do is let's first do when we are not, so let's let's use cache as false, so that we have a baseline, like how much time does it take normally if caching is not enabled. And then next we will enable it. We just have to switch the flag. I believe it's going to take some time because it's doing the about, I think, 7 or 10 runs. Then we will be able to, so it says it takes about 4 seconds median. So let's see if what happens when we set cache to true. I believe it should be faster. Yeah, so see, it's about like 1/3 of the actual speed. So this is much more faster when you enable the KV caching. And so this is something that's that you should see and explore more from your end. And in this session we were able to look more inside the transformer model, the model architecture, and how can you do the KV caching. Thank you very much for, let's see you in the next session. What I have been seeing lately, that people are using simple stuff where a text classification can be used. So now today we are going to do this. Let's connect your T4 machine and install this dependency, because we are going to build our own text classifier from scratch without needing to call any API endpoint. So text classification are where you are using a language model and trying it to make to certain classification, whether it is positive, negative, or any type of keyword classification. So this is what we are going to do here. Let's load the dataset. Let's take an example of Rotten Tomato dataset. It's a public open source dataset that we can use with the help of transformers load dataset function. Oops, I made a mistake here. Let's first install. Make sure do not forget to install it, and then import it from datasets, load datasets. Once it's done, let's run it. Once you execute this code, it's going to load the entire dataset for us in a very convenient way, where we will already get the data in the form of text, test, train, validation. So just let's see one of the entry of the dataset. See, you have a text and then you have a label. Now where the label 0 means it's a negative review and 1 means a positive review. So this labeling you already have. Perfect. This is what we want for supervised fine tuning. You need data in this form. Alright, so let's begin. Just see, you have train, test, split, validation already prepared for you. Now let's create the pipeline as we have done in the first chapter. Let's also return all of the scores, and let's see if we are connected to the GPU. Perfect, we are. And let's execute this code. It's going to take some time. Meanwhile, I'll explain you what's happening, but you need to also specify the model path. So that I have done it again here, and this time hopefully will not have any error. Perfect, it's loading all of the models that we want, this safe tensor and all. Now what I am going to do is to write some helper function which is going us to use that pipeline, and then what we want to stream this text that we have into that text pipeline. So for that we'll use key dataset, and we are going to let's pass a smaller dataset for this tutorial. Test1, let's collect the negative scores, the positive scores. And so reason why I'm using 0, 1, 2, because this model predicts 3. It also predicts the neutral one. So that's why since our data labeling is in the only 2 labels, it's better to use that way. So as you can see, the training is completed and we are able to see our predictions over here. Sorry if I said training, it's actually we are just doing the only the prediction for now. So this is an helper function which is going to generate the classification reports from a scalar. We are interested in knowing the F1 score and all of these things that we just got from the above. So let's pass the label. So and also we'll pass our ypred that we just calculated above, and let me type it ypred and let's execute it. There you can see we have a good performance actually. So the model is quite good given it has been trained on the Twitter dataset, but it also works for our Rotten Tomato dataset because it's transferable. So that's the important thing. Alright, so now what we are going to do is to try another model. Let's use sentence transformer, and let's do embedding based approach. So from sentence transformers, let's import sentence transformer, and then let's also bring our model, which is all MPNet base v2. It's actually quite good model when it comes to text embedding. So let's calculate the training and test embedding using model.encode, and then let's also show the progress bar. Same thing we do it for test as well. Perfect. So once this is done, let's also print the shape. I assume it's about 768. Now let's do one thing. Let's pass all of this through a logistic regression model, and let's train that classifier and see if we are able to improve what we have seen above through a vanilla model to a logistic regression model, prediction from there. So what we are doing, a classical machine learning on top of our embedding. And after that we are going to call the same helper function that we have made. Again, I have to just remove the s. Yep, yes, let's call it again, and we can see it's now it has better performance. And now let's run it. So what I am going to bring some of pre-written code over here. What it is doing, what I am trying to prepare is a zero shot classification using labeled embedding. So let's use the data frame, and so what I am doing is appending label as column index 768 because we have the embedding 767, and then just group by with the mean and take an average, so that we'll have all of the samples, mean embedding and the sample itself. And after doing that, we will be able to calculate the cosine similarity without even training that model. And let's compare, if we don't train a model, what will be the performance of it. I believe it will be low, and then that what we are seeing. So let's now we are going to call that model dot encode on a negative or a positive review. Let's see its performance, and let's do one thing. Let's call the cosine similarity. We have test embedding and its label embedding. Let's collect the verb predictions. Again the same mistake. Let's move the s. Now let me run it again, and then using flan t5, let's evaluate the performance. It's quite down, which is expected because we had trained a logistic regression model which performed quite well. So here's the summary. You should use your own model for such task. Thank you. Hi everyone, so I'm back again with a PyTorch tutorial. Make sure that you have selected your GPU. Install this dependency because we are going to do the clustering examples today. So let's import our dataset. This time let's use the archives NLP dataset because we are going to learn about the topic modeling and all. And let's bring the abstract and title from this dataset because this is what we get. And we only have the train in this, as there is no validation and all such thing, because this is the unsupervised way of doing deep learning. So let's import high quality embedding from sentence piece transformers. We are going to use the GT small model. Why GT? Because it's small, fast and good quality embedding model, and the output dimensionality is quite good. Like, so we usually have about 384 dimensional vector per document. This is what you can expect. So let's see. Let's encode our all of the abstract, and let's also show the progress bar. and let me copy the correct. Let's see, this is quite done. It's going to download the model first and then we are good to go. Let's see the shape. I believe it's going to take some time. Meanwhile, I'll just go to the Hugging Face and look at the model card, and I'll show you like how you can get the exact callable functions. So search this, the model that I'm using, or any model, come to its model card, scroll down, and you'll see how to use that model. So it expects an array, string of array of strings, and then it's the same way that I'm going to follow it. So I'm going to fast forward this, and it's going to take about roughly 2-3 minutes, and in the meantime we will be able to once it is done, and then we can move further and import the UMAP, which is going to be used for dimensionality reduction. And I mean, you must ask like, why embeddings? Because topic modeling is BERT topic, which works on semantic spaces, not on raw text. So for that we'll need to do some pre-processing of this text. So let's from UMAP, let's import UMAP. Import UMAP, and then UMAP, we need to initialize this. We need to specify how many components, minimum distance, matrices. We are going to use cosine similarity and a seed. So this UMAP will compress 384 dimension from above into 5 dimension. Because why? Because we are going to use the HDB scan, which struggle in the high dimensionality, and the topological structure that we are going to see becomes very much clear. And you must ask like, why 5 dimensions? Because it's enough to preserve the structure and faster clustering for 384 compared to 384 dimensions. And the distance I'm picking 0.0 because it allows the tight clustering. It will help us in doing better topic formulation. So let's call the fit transform method of this, and then we will be getting the reduced embedding, and then we can pass that to HDB scan. So meanwhile it is happening, let's import the HDB scan from HDB scan, and let's also initialize this. We need to define the minimum cluster size. Let's define 50 for now, and the metrics we are going to use the Euclidean distance, because now we can compare the Euclidean distance. And the cluster selection method, we will use the EOM. It's better for stability, and then let's call it. So we are calling the correct function. And if you are wondering what is it, there is a very good documentation. What is HDB scan? If you want to understand what is density based clustering, that also you can refer it, and it's a very good documentation to read. All of the internal formula and implementation are present over there to make sure to check this out to have a better understanding. So yeah, okay, so there's one problem. Let's correct this. This is supposed to be equal sign. Yeah, let it run. It's perfect. And now we can see the set of cluster. So let's use NumPy, and we'll use NumPy where look at the clusters and just see the abstract, some of the abstract just for you. to see what actually the input data looks like. Let's see for few words. There is an error. It says wrong key type. 313 is a type of numpy int 64. Okay, expect an integer. So must be an error. This must be occurring during the slicing. So let's try to remove it. Let's try to hit again. Okay, I got it. So we have to actually pass. It is expecting us to pass the integer, but somehow it is sending the numpy int 64. So we can convert that. We'll just need to typecast the indexed as integer. Hopefully it is going to work. So let's do that. See, this is where what I am asking. This is where it's breaking. So let's go there and type int, and it's going to work. Perfect. Now you can see the abstract itself. These are the document that we are trying to create the embeddings visualizations in the topological clustering. So for creating the visualization, we will need to use this reduce embedding, and let's make a data frame out of it. So here's the code. This is pretty much the stuff where we are going to create the data frame, and we actually want to store the UMAP coordinate and cluster assignment. So now from there we can create the cluster data frame and the outlier data frame. And -1 is the HTB scan outlier cluster, which is called the noise point, and we'll plot them separately. And now we can call the plot. I'm at plotly plotting the scatter plots. From there you will be able to see the reduced embeddings of this dataset. So let's call this function. If everything works fine, it should show us the plots of our embedding. Let's wait for it. Yeah, let's run it. There you can see how good clusters have, our dense cluster has been made. See, it's beautiful, honestly, if you ask me. So from the documentation we were able to create such a density based clustering, which is nice. Thank you for watching this session. Bye. Hey everyone, I'm back with one more tutorial on PyTorch. Today we are going to learn about the prompt engineering and specifically focus on local models. So let's import transformers auto model for causal LLM. Let's bring the 4 mini instruct, and we are also going to bring the same tokenizer. I'm going to fast forward it because this is pretty much we are doing from the previous sessions, and make sure to also watch them if you have not seen. Here I'm not doing anything specific. I'm just calling the transformers auto model API, and we are just initializing our text generation pipeline here, which is going to be very helpful. So here what is happening, it's going to load the model first. Oops, so this model does not accept, I guess, the max token in that format. We'll need to look at their documentation. Let's do one thing. For now, let's comment this out. Yeah, perfect. Now it is working. It is loading the model shape tensor. Meanwhile, let me prepare a template which will be used by this model. So see how I am doing. Creating an array of dictionaries, defining role, user, and then giving the context, and then this array is going to be passed into the model. And once this model is done, let's see how much GPU it is utilizing. It's right now the model is in the system RAM. Now it's in the GPU RAM, or taking about 7 gigabytes. Let's run it and see the model output. It should be able to do it. We have just asked and write an article on AI, and it's done. This is what we expect from a language model right now. Nothing fancy, but the important thing is we were able to do it from ourselves through a local model. Now let's learn how to apply a chat template. So let's define, if you can also see from your tokenizer, before tokenization we can see the tags that it assign with this is the thing which is going to be tokenized. So I wanted to show you what is actually getting tokenized here. So the thing, anything that we have written in that format is getting converted to this form. So which is something very nice to understand. You can also replace your prompt here. I am going to, this is a chat template. This is what I prefer, like breaking down everything and then deciding the order. So the main text, this is going to be your, let's say, context that is coming from somewhere else, and then your prompt component like persona, any instruction that you want this model to do, we will ask it to do the summarization, and the context that you want to provide, data format, audience, tone, text, they all are strings, and the text is the one which is, you can assume to be the input. And this is how I make the query: persona, instruction, format, tone, all of them added. Then it's become a single prompt. It breaks your task into multiple subtasks, that for you it becomes easy, and for a model it goes as a single string. This is what I prefer. And then we can just copy the same thing that we did above, and now this time give a proper formatted context to the model. Let's pass our query, and that's same way we will be able to print the tokenizer. Let's apply the chat prompt template. That's this chat template, and then pass the message. Let's see where it has added the tokens and all, and we make sure to tokenize, mark this as false, otherwise you'll only see the numbers. So see, the user and these tags are very much important for an AI model, because after the end of text it is going to do the generation work it is going to do. So now let's also call our pipe and just pass this output, the message, and then let's look at the generated text. Let's run it, give it a second. This should take, oh, there's a typo over here. It should be generated. Let's see if the RAM spikes up during the invocation. It's pretty much stable, so this is a good thing. And here's the model response in the format that we have specified above. I did not waste time on typing the prompt for you. I mean, this is something that you can experiment based on the downstream task. Now let's move forward, and let's copy paste this one shot prompt. This is one of the technique where you give one of the example to the assistant, and then you are going to ask, I mean, before making the invocation you are giving one example, and you can see the user message getting ended, and then the assistant message I have hard coded it here, and so it gives an idea to the model, like, and this is how we expect you to respond on such queries. So the assistant message we are ourselves supplying, and then after user we are expecting it to create an assistant message again with one shot example that we have given, and the same way we just need to generate it, and let's see if it follows the our way of answering, which it does. It becomes very important for a small model. GPT like model, they don't need that much, but their accuracy can also improve for your task. Now let me copy paste one more prompt template that I have. Let me copy. You can give me 1 second, and let me paste it here. Yeah, so let's say this is a product prompt, and this product prompt has a create a name and slogan for chatbot, and their leverage language model. So it generated the from this is what we have seen. Here's is the thing, we are going in the very specific direction that we want very specific things in a certain format from a model. So there's something that just came into mind. Now what we should do from the one shot example, let's see how to do a chain of thought prompt. Here you can see the assistant prompt. I am breaking down a problem solving. So in the next step, what I expect the model to also follow the same. So see, it has done here. So this is what actually happens for the chain of thought models. Their data sets are prepared in such a way where they the assistant message that we type are actually used to guide the model. And now we can also bring what we have learned in the zero shot and caught to make it take it even further. Like, you give examples of steps that needs to be taken, and then it needs to give an answer. So see, it's not a reasoning model, but we just emulated that from here because of the zero shot and caught prompt. This is very effective, and this is something that I wanted to share. It's not about big models, it's about the skills that you need to acquire to build such systems. Thank you very much for following this session. See you in the next tutorial.